Yes, so thanks a lot to Roberto for joining today. Roberto is a PhD student at UDEL, and we had the pleasure to meet a few months ago, and it was a very nice conversation, very nice project. So I hope you enjoy it, and the floor is yours.
Yes, thanks a lot. Thanks also for the invitation and for being here, though, well, online, but still here. So I'll just proceed to share my screen so that at least we can see if you're all seeing it. Do you see it?
Yes, yes, we do.
Perfect. So I'm going to present today the work that have been published some months ago, and you can actually also look at it via this QR code on the first slide here. But basically, it's the first part of what I'm doing in my PhD. By the way, I'm currently doing my PhD, as Maria kindly said, at TU Delft. And I'm working on the interaction between flood modeling and deep learning. So as you can see from the title of my presentation, this is rapid spatio-temporal flood modeling with hydraulic-based graph neural networks. I will spend most of the presentation in terms of describing what this hydraulic-based model looks like. So first of all, since not everyone might be familiar with flood modeling, I will just briefly introduce why do we care about flood modeling. So let's see if this works. Yes. So the easy answer is, well, flood risk. So what we care about is to determine which areas are affected or could be affected by this particular danger, in this case, floods. And we care about which lives are at risk, which economical assets are at risk, and then we can develop some mitigation strategies, some prevention strategies to decrease this risk here. That's one big main application for flood modeling. And the other one is with early warning systems, so that we can basically, oh yes, there it is, so that we can predict in real time where and when a certain flood will occur. So these are two of the main applications, not comprehensive, but two of the most relevant ones for flooding. And now the issue is that the numerical models, which are the ones that are commonly used for this kind of applications, are computationally expensive. So at least if we want an accurate solution, we're going to spend a lot of time. And this means that for flood risk, where we have to run probabilistic analysis, so we have to run a lot of simulations, this is not feasible. And as well for early warning systems, we want something that runs in real time. And those two characteristics are not compatible with computationally long times. So that's work here. Yes. So that's the motivation for this work. What we try to do is to have some model that is as accurate as numerical models, but faster. And what the literature suggests is that deep learning can be one method to accelerate these numerical simulations. And this doesn't hold only for flood modeling, but also for any other kind of simulations, to be fair. There's a lot of examples. Recently, there's been a lot of focus on weather forecasting, less in terms of accelerating the simulations, but you can see that deep learning models can be very accurate and can be very fast. The problem, at least in terms of flooding, but this holds also for other fields, is that many models cannot predict the spatio-temporal evolution of floods. And this is relevant, as I mentioned before, for determining when and where a certain flood will occur, so that we can determine some evacuation strategies, for example. But mainly, the most important gap that most deep learning models have is that they're only usable for one single case study, one single topography. So we have to train our model on one area, and then we cannot apply it on any new area, which makes it ultimately less useful. So what we plan to do with this research here, basically, is to have a model that can predict both the spatio-temporal evolution of floods and can work for unseen topographies, so that we don't have to retrain every time this new model. Now, this is an overview of how the model looks like. I know it's a lot of information, so let's go one step at a time. First of all, what does the model take as inputs? It takes more or less the same inputs as a numerical model. So we have some static inputs, which are basically properties of the case study that we're modeling, the topography that we're modeling. So there's some elevation information, some slope information. You can add some roughness, so land use information. And this property doesn't change in time for a given case study. It changes across case studies, but not for a single one. And then you have dynamic inputs, which are basically representative of initial and boundary conditions, at least at the beginning. And you can see, for example, here that as initial conditions, we can put a dry bed domain, so no water in our map. And there's some boundary condition in this case of water depth and discharge at the beginning of the flood. And what we want to do is predict the evolution of this water depth and discharge, which I'll just call hydraulic variables, at the next time step. Then we use the model output as a new input, as you can see by this arrow here, and we repeat this operation autoregressively a lot of times. So we always use the output as a new input until we cover a desired portion of space or a desired prediction horizon t. Now the tricky part is how to go from time t to t+1. And this is how we do it. Again, a lot of information, but what I want you to focus on is this part here, the GNN, the graph neural network part. The rest of it, what it basically says is that it's expanding the dimensionality of our inputs. Since we have 7 inputs, for example, in this case, we want to expand a bit more the dimensionality to get more expressivity, more representativeness of the inputs, and then we decode them at the end to get an output which is compatible to what we want to predict. In this case, water depth and discharges. But the main operations occur in the center of this model, this graph neural network side here. Now, you might be wondering, why do we need the graph neural network? And most of all, where does the graph even come from, right? Well, the answer comes from numerical methods. So I didn't mention it, but my background is mostly on numerical methods, mainly with floods. And what we do with numerical methods for floods is that we solve the shallow water equations, which are basically the Navier-Stokes equations in 2 dimensions, and they represent mass and momentum conservation of our flow. And we discretize these equations, which can look something as this line here. And we also discretize the space that we're considering using a mesh. Then generally we use a finite volume method to solve this combination of discretized system and discretized equations. And then what we're doing with this is that we're determining the hydraulic variables, how they are evolving in time at each cell in our mesh. So this is mass and momentum conservation. This summation term here, you can see it as the fluxes being exchanged from one cell to the neighboring ones. And the problem with numerical methods is that generally this time step here is quite small. So this means that this operation has to be carried out a lot of times for all of the cells in our domain, which is what makes it slow, ultimately. So the idea is, what if we could sort of approximate this whole function for large time steps? This is what it would look like. I just changed a bit some variables, but you can see that the structure is the same. Now we just use this function f to approximate everything that is going on here, which is the solution of mass and momentum conservation. Now, this equation here is an instance of graph neural network. If you're familiar with graph neural networks in general, with the message passing terminology, for example, you might see this function here as a learnable message, and the node update function is just a summation, and with permutation operation sum. But again, it's doing the same process as before, but now the graph is not the mesh itself, but the dual graph of the mesh. So what does this mean? Is that we have cells which are represented as nodes, these points here, and these nodes have as properties everything that is embedded in the cell itself. So for example, its value of the area, the value of elevation of that cell, the value of water depth at that cell, and so on. And you can see it for all kinds of variables at a certain cell. So this represents a portion of space. And we connect neighboring cells via edges. So what this function here is doing is propagating some information, x, in our case water, from one node to its neighboring ones. Now, this function here is where the tricky part comes from, because this has to approximate mass and momentum conservation, which is where the problems are, let's say. So what do we choose as function f? The easy solution will be to just plug in all of the inputs into a learnable function, for example, multi-layer perceptron, which is basically just, well, a sequence of linear models plus some non-activation function. And yeah, this can work. This gives some results, but we can do more. We can add some sort of physical bias to our simulation. We can add some properties that we know are intrinsic of our model. In particular, this term here. So what does this term do? First of all, xd is what we called before the dynamic input. So it's a representation of our hydraulic variables. This is going to be 0 if there is no water and non-zero if there is. So what this means is that if two neighboring cells are empty, there is no water, then there is no propagation going on, because these two terms are 0, and the whole fluxes that are being calculated, this f function, are going to be 0. So what this additional term does is it prevents water from coming out of random points in the domain. The other motivation that we have for adding this term here comes more from numerical methods. So in numerical methods, you determine fluxes based on the Jacobian of the approximated Jacobian of the fluxes times the hydraulic gradient. So in this case, we can assume that this learnable function phi is some sort of higher dimensional Jacobian of the fluxes of mass and momentum conservation. But in practice, well, we can actually just say that it resembles it. We can't really prove it too much. But it gives a link also to what is already existing in numerical methods. So that's it. That's the model. Now, I mentioned before that this f here, this function f, should work for any time step. By the way, if you have questions, please just interrupt me, and no problem. So what this function f here does is approximates the fluxes, right? But in numerical methods, we use a small time step because of this CFL condition, which guarantees numerical stability. So the time step has to be proportional to some constant times the discretization of the mesh divided by some flow propagation speed. Well, in our case, we want to do it the other way around, not determining the time step based on the spatial discretization, but vice versa, because we want this function to work for a given time step. So we would want something like this, which is basically the inversion of the equation of before. And this in numerical methods would result in increasing the size of the mesh, because there's no way that you can increase the space without just changing the size of the mesh. In the case of graph neural networks, we can avoid changing the size of the mesh by just stacking multiple graph neural network layers. And let me show you how. So assuming you don't have any graph neural network, then you're just doing node-wise functions. When you're adding one layer of graph neural network, you're taking into account the neighbors of this cell. When you're having two graph neural network layers, you're doing the neighbors of the neighbors, and so on. And so you can see that within one function, one iteration of this operation here, you can reach larger portion of space without having to decrease the time step. And the reason why this works at least sufficiently works, is that the time step constraint usually is needed only in some specific portions of space where, for example, the cells are smaller than the rest of the domain. So we can sufficiently say that this approximates well enough the propagation for a given time step. I will show you also some results on this later on, but for now, just trust me. And so that's it. That's the model and explanation of why it should work. Now, in terms of training of the model, we have a problem in the sense that our modeling problem is a bit complex. We're doing a spatio-temporal simulation, and we're doing it for a lot of time steps. So one way to reduce the loss that could be accumulated over time, the errors that could be accumulated over time, is to do a loss when training our model that takes into account multiple steps ahead. So not doing the loss only from time step t to t plus 1, but also including t to t plus 1, t plus 1 to t plus 2, and so on. And it will look something like this. So at the first iteration, we're starting with some known inputs, and we're predicting the evolution at time t plus 1, p plus 1 in this case. So now this p plus 1 here is predicted. It's not true value, but it has some sort of error. Now we can take this as a new input and predict the next time step, and so on. And you can see that at some point, our inputs will all be given by the predictions of our model. So if we didn't do a loss on the summation of the mean of these terms, we would keep on accumulating errors. The problem with doing the loss on all of these time steps in one go is that if you take too many time steps, this error here will already be too large. And this means that even if you have a very small learning rate, your model will not be able to learn because there's so much accumulation within these steps here that it won't work. So what do we propose as a solution to this? Because as I said, we need to minimize the loss over multiple time steps, is to use a curriculum learning strategy. The idea of curriculum learning is that you start with something simple and you progressively increase the complexity of what you're training on. In this case, what we're doing is that we're training first the model to predict only one step ahead. So first we want to predict well from t to t plus 1. After this is done, after a certain number of epochs or after a certain threshold of loss, then we can move on to predicting as well the next time step. So at the beginning, we'll only do the loss on time t to t plus 1, and afterwards also from t plus 1 to t plus 2, and so on. And we can do this with this sort of algorithm, which basically just says that after a given number of epochs, you can increase the number of steps ahead that you want to do your loss on. There's a lot of different curriculum learning strategies that you can use. In this case, we used a strategy which is based on the number of epochs because there was not much difference with other learning strategies, and this was a bit more consistent even independently of the value of the loss that we're getting. Yeah. So that's it. That's the model, how we trained it. And now let's see on what we applied it. So as I said before, we want to do flood modeling, but in this specific case, we're focusing on dike bridge flood modeling. So dike bridge floods are basically when dike are a levee. It's called in different ways in different countries, but when this flood defense that protects us mainly from rivers or from coasts breaches. So there's a point in which this defense breaks, and then water comes in from that single point. And this is one of the most relevant flood hazards in the Netherlands, at least. So that's why we selected this case study. To assess the validity of this model for unseen topographies, we created a dataset using randomly generated digital elevation models, so different topographies. In this way, we have a lot of different samples, and we can train on different configurations of topography and test as well on them. And for this specific instance, we're using a regular grid mesh instead of an irregular one to allow for the comparison with other models. So in this case, the regular grid will look something like this. And this allowed us, for example, to compare as well with convolutional neural networks. Now, we don't want to only show that this model works well with different topographies, but we wanted to show that this model, because of the hydraulic bias that it has, works also in generalizing to different conditions. So the first dataset is, as I mentioned now, with different topographies. There's a lot, 100 simulations split into 60 for training, 20 for validation, and 20 for testing on a domain that is 6 kilometers by 6. And in each of these simulations, we're giving a constant bridge discharge in the bottom left corner of our domain. Then we want to test as well in domains in which the bridge happens in different locations. So this will show that the model has learned not only that the flow only starts from the bottom left corner, but there's some dynamics of how the flow moves, and then it will be independent of where the flood starts, because just learning the dynamics of the flow. And we also wanted to see how well it goes when generalizing to bigger domains and longer time steps. So we also created another dataset which is 4 times as big as the training one, has varying bridge locations and a longer simulation period. And this is how it looks like. So this is one of these randomly generated elevation models. So it's random, but not completely random noise. It has some sort of resemblance with a plausible topography. And this has never been seen before by our model during training. So this is something completely new. And as I said before, we have an inflow coming from the bottom left corner of our map. And this column here represents water depth and discharge of the numerical model, so what we're trying to predict. And these are the predictions of our deep learning model, with the differences on the rightmost column. So as you can see from this video, there are some temporal lags. So for example, the model is under or over predicting at some certain time steps, but then it tends to correct its own predictions, so that overall the patterns in space and time of how the flood evolves are quite well approximated. And again, this is a domain which has never been seen before by the model. But this works not only for bridges that are coming from the bottom left corner where the model was trained on, but also from random places. And again, as before, there are some differences in when the flood reaches some points, but then the general distribution of the space of the floods in space and time is well represented, even though it has never been seen before. And also for bigger domains. So we can see here that now it's 12 kilometers by 12 instead of 6 by 6. And now it's prediction time of 5 days instead of 2. And you can see that nonetheless, the model knows where and when the water should go. This takes a bit longer because it's, well, 5 days. But overall, the patterns are there. There are some mistakes here and there, but generally, those are mainly due to what, as I said before, to temporal lags. So for example, there are some portions that are flooded in the numerical model and not in the prediction one, in the deep learning one, but probably those will be covered at the next time step if we just keep running the model. So there might be some variations, but overall, the patterns match quite well. So this, okay, works, but how about the speed? I said we want something that is also fast. And what we can do is to determine a Pareto front of different model configurations. So what we change here in these different points, X's and circles, is the size of the model in terms of number of parameters. So for example, we're changing the size of the embedding in the from the encoder of our model, and the number of layers of graph neural network layers. And what you can see here is basically that bigger models are better but slower. So you can decide which model to use depending on the application and depending on what you care about. If you want something that is faster but more faster but less accurate, then you can go for something a bit higher along this curve here. Or if you want something that is accurate but you don't care too much about the speed, or for example you have a GPU, then you can select just the bigger model. But the point is that you have a range of models depending on the application, and all of them are faster than the numerical one. As I mentioned before, there was this let's say this claim that you can avoid the CFL condition, the numerical stability condition, by just adding more graph neural network layers. And what you can see from these plots here is for different temporal resolutions of the model, so for different time steps, the number of layers needed to reach a good level of performance increases with the temporal resolution. So for example, in the first case of 30 minutes, 1 times 1 layer is as good as having 2 layers in the other temporal resolutions. So the point is that the number of layers in the graph neural network is proportional with the temporal resolution. And the more layers we have, generally, the better the model is. And finally, we also use these 2 different training strategies combined together, the multi-steps ahead and the curriculum learning. And what we can see is that basically from this plot, you can see that adding a longer prediction horizon in the loss helps with the overall performance of the model. So with 1 step ahead only, the model is much worse than with just for example, 8 steps ahead when training. And same goes for the curriculum learning. It both helps with so basically what is saying here is that we're changing these values here, 0, 5, and so on, are the number of epochs after which we're changing our curriculum step, after which we're increasing the time steps in the training. And what this says is that obviously the higher you have this curriculum step, so after which you are changing your number of steps ahead in the loss, the faster the model trains, because you're spending more time on a simpler problem, on just 1 step ahead instead of 2, 3, or so on. And it also improves the performances when you go to a certain value of curriculum steps. But okay, so this is basically what has been done so far in the paper, but this had some limitations. So since I had the time, I will also show you some, let's say, augmentations of what has been done until now. So first of all, this method until now was applied to regular meshes using stationary boundary conditions. So we have a constant inflow discharge. And we also needed, I think you might see it, for example, from here, we needed some sort of input from the numerical model to determine where the flood starts from, because we don't have a proper treatment yet of boundary conditions. So we're still sort of dependent on the numerical model. But we can deal with all of these things, or especially with boundary conditions, using ghost cells. So it's the same idea as before. We're still discretizing our domain with a mesh. And as we do in numerical models, we add this ghost cell, which is basically a cell which is not part of the domain, but still part of the computational domain. And in this cell here, we're applying external values. In this case, for example, we're applying a certain value in time of the discharge, of water level, or so on. And then we can apply a sort of directed edge if it's inflowing towards the graph or outflowing on the opposite direction. And this will help propagating a given discharge without needing the first time step of the numerical model. To deal with irregular meshes and time-varying boundary conditions, we also improved the model by going to multi-scale methods. I will go more or less fast on this, but the idea is sort of the same as in UNet-based convolutional neural networks. So you start from a fine scale on which you run your numerical model, and then you progressively pull to coarser meshes, and then you go back to the fine scale. And at each of those steps, you're applying a graph neural network that propagates the flow independently at each scale. So you have, in this case, 4 scales, means 4 graph neural networks that I just described before. So it's 4 times as big model, but actually it doesn't matter too much because the number of nodes is larger here. So if you have a very big model on this coarse mesh, it doesn't really affect as much the computational time, because the number of times you're operating that graph neural network is much lower than the ones that you're applying it here. And well, this can go a bit more into depth, but it's still sort of current progress research. So that's not maybe the final architecture of it, but it's sort of the idea of having propagation of flow, in this case, at different scales. And the idea is that the propagation speed will also be different at different scales. So this will be helpful when dealing with time-varying boundary conditions, because in time-varying boundary conditions, you might have very different speed of propagation. And so this means that, for example, at the coarsest scale, you have a much faster speed of propagation, because you can see that you're covering much bigger portions of space, even with just one operation of the graph neural network. While, for example, to cover the same space in the fine mesh, you will need much more steps of the graph neural network. So this is a high-level overview of how the model looks like. And I can show you already some results on this. So again, this is, well, this is work in progress. I will explain now why, but it's the same setting as before. Now we have a time-varying boundary condition, and this is how the model looks like. So it can predict very well where the flood will go and when. And this is what's happening sort of under the hood. There is a lot of different scales at which this operation is done in parallel. So the same thing that's done before, but now we have 4 graph neural networks that are connected one to another. All of them are doing this sort of propagation at different scales. And this helps in connecting the boundary condition to the rest of the domain. Now, as I said, this is work in progress because this is actually one of the training samples. So it's not completely fair. So I will show you also one of the testing ones. This is instead, the one before was the model was trained on, this one here not. So there might be still some errors, but overall you can see that the dynamics are well captured. There are some, in this case, problems with the propagation because of the different shape of the hydrograph. So it's not left right-tailed as before, but it's right-tailed. So the way the water propagates in time is different. So that's why there are still some limitations. But overall, you can see that the model works well, despite not having any input numerical model, despite not knowing beforehand this specific mesh and this specific domain, and the domain being also quite irregular. So as a summary, to wrap up, some main takeaways of this presentation is that graph neural networks are a valid modeling choice for problems where finite volume methods are used, which means that in this case, we've used them for flood modeling, but in principle, you could use it for any other flow problem in which finite volumes are generally used, because the method is inspired by finite volumes and it's discretizing a specific partial differential equation, but it can be applied in the same way to other problems. And second of all is that using this kind of training strategy with curriculum learning and multi-step ahead loss improves the stability of the model and the performances, while also being faster in training. And finally, as a conclusion, yes, we have proposed this new graph neural network model, which is inspired by hydraulics, basically, and it can generalize well the spatio-temporal evolution of dike-bridge floods over unseen topographies, unseen bridge locations, bigger domains, and longer time steps, even without the use of any numerical input. And it's also up to 2 orders of magnitude faster than the underlying numerical model. So what to do now is to basically apply it to some case studies, which is what we're already working on with a master student to apply it on dike ring in the Netherlands, so Levy systems here in the Netherlands. And that's it. So thanks for the attention. Are there any questions?
Excuse me.
Yeah.
I have a question. So if we increase the number of graph neural networks in the whole model, is it prone to overfitting at some point, or we will always have too much data so it never perfects?
I would say that it shouldn't overfit by the fact that, well, in this case, I'm also there's a lot of data that is being used. Despite being a limited number of simulations, each simulation has a lot of cells and a lot of time steps. So actually, one single simulation will comprise, let's say, this had 10,000 points times 48 time steps. So one single simulation is almost 50,000 samples, sort of, in that sense. So the problem of overfitting is always there, but up to a certain point, let's say. We can always try to go for smaller models, and then you can trade off depending also on how the performance is going with your validation dataset.
Thank you.
Question. Thank you very much for your presentation. I really enjoyed it. So I've actually got 2 questions. One is the constraints that you use to train your graph neural network are all local by construction. But
Yeah.
I was wondering whether you can add in global constraints. In your case, for example, a constraint would be the volume of fluid is conserved.
Yeah.
Can you do that?
You can do that. It's not shown in here, but you can add some sort of mass conservation globally, so you can conserve you can do the loss on the difference between the inflow volume given by the boundary conditions and the volume that you're predicting with your model. The results so far indicate that adding this term doesn't really help much, but I have to still explore it a bit more. But okay, you can do it for sure.
Yeah, okay, thanks. And my second question was on the practicalities of your work. Can you say something about the code platform that you used?
Yeah, so I developed everything in Python using PyTorch and the PyTorch Geometric as libraries to develop the model. And actually, the repository is as well online. You can find it along with the paper that is being showed in the first slide. I should have put it also in the first one, I suppose. But basically, there's already a repository of all of the data set that I used, all of the trained models and so on that I used. It's blocked. Well, yes. Small presentation. Okay, here. So yeah, there is all of the code available. Well, this was the code done a year ago, so it's not directly suitable for the result I show you now with the boundary conditions, basically. Now I actually changed all of the code there into PyTorch Lightning to have it a bit faster as well. But that code adapted a bit can work easily for the problems I showed you now.
Great, thank you. Sorry, can I ask another question? It's about the training. So you commented that your networks are about up to a factor of 100 faster than the native numerical models. But how long? I guess that doesn't take into account the training effort. So can you say something about that?
So I don't remember exactly the training times of the previous configuration. I can tell you the training times of the ones I'm doing now with, at least with the multi-scale method. And for training, the model was right now was training only on 20 simulations on a 32 GPU. It takes 1 hour to train the model. So it's not too much. It's also not as rapid as other models, obviously, but still, for being a very big model, it's relatively fast. Obviously, you can go for bigger models, and then it will take longer. But the one that I showed you now took approximately, let's say, between 1 and 2 hours.
Thanks.
Yeah.
Right. Thank you. That was a really interesting talk. Now, so far, you've shown us how it works for simulation data. Could you comment a little bit more about the practicalities of implementing this in the real world? And in particular, can it be used in real time, so in a data assimilation step for observations of how floods have evolved, and also taking into account any human interventions that come into play in the event of a flood?
So thanks for the question. I will say, well, right now the model is still probably not in the stage of being used for real case studies, because it has never been trained on something like that. But it would just be a matter of training it on some more realistic case studies. And then if you have a GPU, you can just run it in real time, and you can run it also a lot of simulations in parallel. So if you knew, for example, that you have a bridge that is about to form in a specific place, you can run it in, I think, a couple of seconds. If you have a GPU, in a couple of seconds, you run a lot of simulations in parallel. And then in that sense, you can have a preliminary analysis for early warning systems. And that can be also done to take into consideration human intervention. So if you add those human intervention, for example, as different elevations in your model, then the model should take that into account as well, because the elevation is one of the key factors in how the water propagates. So technically, you can do it. Practically, I cannot guarantee it because I haven't tried it yet, but it will make sense that something close to what it is right now can be used in real practice soon enough, hopefully. I hope that answered the questions.
Yeah, that's great. Thank you.
I have a question. Hi, thank you for your talk. I was wondering if you can expand a bit on the training, specifically the multi-step training. So I found multi-step to help, but for the work that I do, but curriculum learning, I don't find it to help that much. So is the curriculum learning helping with stability, or is it helping with the overall prediction of your result?
So the way curriculum learning helps, it does it in 2 ways. First of all, it makes the training faster, because, well, you're starting from a sample which is just 1 step ahead instead of, for example, 8 steps ahead. So you have it not 8 times faster, but sort of like that. So you can have already a sort of, you could say that that's a sort of pre-training of the model, or then going into a more complex stage of the training. So that helps in terms of speed, but it also helps, at least from the results I had until now, it helped because sometimes you had an explosion Other questions?
People online could mute themselves.
But it also helps in if you have a model that is by chance, let's say, initialized in a bad way, then you will start with a lot of errors. And if the learning rate is not small enough, then those errors will struggle to be minimized in a good way, as if you were doing it with the curriculum learning. At least for the number of steps that I tried, that was the case. And especially, I think if you go for longer time horizons in training, then this might be a more frequent problem.
And also, how did you prevent over smoothing with your graphs? Because you showed a plot where you increase the number of layers and your error reduces. Did you experience over smoothing at all?
No, not really. I think the reason for that might be that the graphs themselves are quite high, are quite big. So there is no risk in that sense of just going through the same nodes a lot of times, as it will happen with oversmoothing problems. So if I were to have, let's say, a much smaller graph, for example, the one in the course mesh that I showed before, and I had a lot of layers there, then that problem of oversmoothing might happen. But in the cases until now, the number of layers was much smaller than the diameter of the graph. So there was no problem of repeating too many times the operations on the nodes. At least this is what I experienced with this particular problem.
Yeah. And just one more question.
Yeah, sure.
So when you're only predicting a single time, right?
Yeah.
And then you pass in that time. Did you ever try multi-step prediction where you're doing a temporal bundling prediction at all? Because I found that they help with the overall accuracy and even speed as well of your training. I don't know if you've explored.
Yeah, so I actually haven't explored that, but it's something that I wanted to check out because indeed it will be easier because you have less steps ahead that you're doing as well in the execution of the model. So that could be something that is interesting to try out. But right now I haven't done it, so I cannot say if it's going to help or not.
Thank you.
Thanks.
Is there someone online with a question? In the meantime, well, I asked you already a lot of questions when we met, but I also have another question on the new work you're doing. When you have the multi-resolution, might be a silly question, but do you think it's possible for a user then to choose, because with the resolution comes more computational time also for the graph?
Yeah.
Would it be possible for a user to have one model and then choose how course to run and solely to use that component of the model? So if you wanted to use a coarser model, then faster.
So in the current formulation that I have right now, not really, because all of the scales are independent one on another because they're connected. So there is a separate model for each scale. Maybe it's best if I go through that image again. There's a separate model at each scale, but then they're also connected. So the propagation at one scale influences the propagation at other scales. So right now you need all of the scales together. In principle, you could also have a model that instead sort of runs just in parallel, but then you miss the interconnectivity across scales, which is what helps in preserving the boundary conditions after longer time frames. But you can just even retrain your model without considering this fine scale, and you consider, for example, a coarser scale as your fine scale. And then you might have a model that is just coarser.
So just to expand on that. So how do you, with the downsampled sort of lower resolution, do you just downsample or do you randomly sample from? When
I move from fine to coarse, in the current setup, I'm just doing a mean pooling. So it's the simplest form that you can do from fine to coarse. And what I saw that this does as well also experimentally is that it preserves a bit the solution at the fine scale. So if there's some wrong result that has been propagated to the coarser scales, basically they get overwritten by this process here. So then it gets a bit more stable with regards to weird propagations at coarser scales. But you could learn it as well, this step here.
Excuse me, it would be a stupid question, but let's say if you have a coarser scale and looking at the unit diagram, can you have an architecture which takes a coarser scale and gives you more like fine scale? But it has like a
technically, yes.
So they can like have lower parameters, but at the same time, it's giving you better predictions on even like finer data.
Yes, so technically, yes. Practically, I haven't tried it, so I'm not sure of how that would work. But yeah, practically, you can have a model that just sort of skips the, let's say, the computations at the finest scale and just uses the other scales to do the actual propagation. And then it will be surely faster because, well, you're skipping all of the propagations at the fine scale, which is where most of the computations are done. But there's a lot of architectural choices when you're moving to these sort of methods that, yeah, you can really spend months and months on just checking out different things. So that's a problem with, well, deep learning in general. There's so much choice.
Yes, thank you so much.
I'll ask another question if we still have time. Can you just talk about things in terms of like training the model, things that didn't work that you tried, and if you have any advice? And
yeah, so good question. So first of all, at least in terms of I will discuss it mainly with regards to this model here, but maybe I can try to first start with what didn't work with this model. So I think that, well, actually in this model here, I don't remember exactly what were the issues, because then there was obviously a lot of different trials, but one thing that helped a lot to have good results in this model here was to add that hydraulic component in the learning part. So sort of the this term here, this difference in the gradients in this hydraulic gradient basically helped a lot in getting better results, because before what would happen is that water would just start filling up from the bottom, from the lowest points of the topography, it would just start filling up. So the last time step would look fine, but the dynamics of the problem were completely wrong. So that was the first, surely something that helped a lot in this previous case. And what regards this multi-scale architecture, I was first doing the propagation instead of from fine to coarse and from coarse to fine, the other way around. And that didn't help. I just tried it out to have some sort of comparison if which direction would work better. And there's other things here and there that affect the model, but they're sort of small things. For example, some sort of activation functions are better than others. Some set of hyperparameters are better than ours, but yeah, there's no critical choice in, let's say, there's nothing that I would somehow recommend to skip. Yeah, right now I don't remember a specific thing that compromised a lot the results, except that term that I mentioned before about the hydraulic-based component.
And with the hyperparameters, did you play with the sort of learning rate at all, or you just that worked? Yeah, okay.
For the learning rate, I'm also using a learning rate scheduler right now with a step learning rate scheduler. And even there, I had to play a lot with the learning rates, because too big learning rates obviously wouldn't work at all, and too small ones would would work, but very very slowly, or sometimes even didn't work that well at all. So it's always tricky, but there's, let's say, there's a good range of values that can work. There's not just one single value that compromises everything else.
Thank you.
No problem.
Well, I think, yeah, we got around the time. So Sam also shared your GitHub, and
Oh, yeah.
so please have a look. It's a very professional code. All the data there are not in GitHub but in Zenodo. So the data, I think, are there.
Yeah, there's everything everything is written also in the GitHub repository to just replicate all of the results that I had here. Yeah, I'm not a huge fan of that repository anymore, even though I wrote it, because it's been written like a year ago. So I look back at the code and I find some things a bit that could be optimized, but well, it runs, so it should be fine.
Okay, well, that was amazing. Thanks a lot for joining and presenting your work. And yes, we're gonna put this the video in YouTube as well, and
Yep.
So more people can watch it. And if you want to contact Roberto, I'm sure he will be
Yes.
willing to discuss further. Okay.
Very much available.
Well, thanks, Roberto, and have a nice.
Thanks a lot again
nice
for the
day.
invitation. I see you. Bye bye. Have a nice weekend.